Okay, this is a problem from section 3.4 focusing on the second derivative on concavity, and we're going to use this polynomial function f of x equals 3x to the fifth minus 5x to the third for our example. The first thing it asks us to do is to use the second derivative test to determine any local extrema. And so our first step is to find the first derivative, which would be 15x to the fourth minus 15x squared. Then we have to find the critical numbers, which would be where the derivative equals 0 or does not exist. Since this is a polynomial function, it will exist everywhere. So we're looking for the zeros. So setting it equal to 0, I will factor out a 15x squared, and we're left with x squared minus 1. Using the zero product property, we would set each factor equal to 0. We would get 0 and then plus or minus 1. So in using the second derivative test, we would have to find the second derivative. So here's the first. So we have 60x to the third minus 30x. And now we'll take each of our critical numbers and we'll evaluate them in the second derivative. And we'll look at the sign. We'll start with 0. And we end up with 0, which means there is no conclusion. When we substitute negative 1, we would get negative 60 plus 30, which would be a negative number. And since that is less than 0, that tells us that the graph would be concave down when the second derivative is 0. So that critical number is a relative maximum. And when we substitute, that should have been a second derivative mark there. When we substitute 1, we get 60 minus 30, which would be a positive number. And when the second derivative is positive, the graph is concave up. And so that critical number would be a relative minimum. So there's our second derivative test for extrema. So now, in terms of curve sketching, we're going to look at the signs of both the first and the second derivative. I'm going to use a number line here. So for our first derivative, we have critical numbers at negative 1, 0, and 1. And at each of those, the first derivative is 0. And now we're going to look at the sign in the different intervals. If I substitute a number like negative 2 back into our first derivative, it would be positive. Any number between negative 1 and 0 would be negative. Between 0 and 1, we would also have negative, and then beyond 1, positive. So our conclusion here is that the function is increasing, decreasing, still decreasing, and then increasing. And so where our first derivative changes from positive to negative, we have a relative max, and where the first derivative changes from negative to positive, we have a relative minimum, which is exactly what we found over here with our second derivative test, that at negative 1, a max, and at positive 1, a minimum. So now we want to look at the concavity, and so we will find the zeros of the second derivative, the critical numbers, and I will factor out a 30x. We're left with 2x squared minus 1. And again, using our zero product property, we get 0. And here we would end up with x equals plus or minus root 2 over 2. So similar to what we did here with our first derivative, we're going to use a number line. And we're going to look at the sign of the second derivative and use that to make some conclusions about the graph. So if I substitute a number less than negative root 2 over 2 back into our second derivative, the sign would be negative, 0. A number between negative root 2 over 2 and 0 would be positive, 0. We have negative again, 0. And then positive. And again, each time I'm substituting a number in those intervals, back into the second derivative and figuring out the sign. So our conclusions here is that the graph is concave down, concave up, concave down, concave up. And each time the second derivative changes sign, we have a point of inflection. So now that I have all of this information, we're ready to sketch the graph. I do want some function values, and specifically I want them at our critical numbers. So I will substitute -1, 0, 1, -√2, +√2 into the function. Let me show you just a quick way to find some function values here on the calculator. So into y equals, I substituted our function back to the home screen. If I hit variables over to y variables function, and then my function was plugged into y1, now when I hit enter, I can substitute values very quickly. So y of -1 would be 2, and I'm going to add those here. So f of -1 was 2, and then I want to find f of -√2 over 2, f of 0, f of √2 over 2, and then f of 1. So I can second enter, and that's going to pull up the previous command, and then I'll just backspace, and I'll substitute √2 divided by 2. And we have an irrational number, so -1.237 going to 3 decimal places. Second enter again. I'll just delete the negative, and I get, this one was a positive, not a negative. So now that I have here -1.237, I can see that f of 0 is 0. And then one last time, I'm going to substitute 1, delete the other values, and we get -2. So I've got the function values that I want. And you would obviously do this on graph paper. I'm going to raise that up a little bit so you can see the whole thing. So we have at -1, -1.237, we have 0, we have +1.237, we have +1, and then we have 2. Actually, this was the y values, my mistake there, so we have a 1.237, -1.237, and a -2. These should have been negative and positive √2 over 2. And so at -1 we have 2. At -√2 over 2 is our 1.237. We have 0, 0. √2 over 2, the negative, 1.237, and then down here 1, -2. So I'm going to take all the information from these two sign charts and these coordinates to sketch my graph. So I am increasing and concave down all the way up to -1. Then from -1 to all the way down to 1, it's going to be decreasing. So now it's just going to be a change in concavity. So it continues concave down. It goes concave up to 0. It then changes concave down. And it remains concave up. And then the next change in direction is at 1. And then it would continue. So again, we have increasing all the way to -1, decreasing all the way to 1, relative min, increasing after. And then you see our changes in concavity as we go along.